In this video, we will compute the 3 kinds of t-tests and then also compute power analyses for 2 of those types of tests. So first we just need to set things up. We're going to be reading in 3 packages. CAR will use to compute the Levine's test to check for equality of variances in our independent samples t-test. Compute.es will use to compute effect sizes, and the PWR package we will use to compute power. And then we need to read in our data, and we're going to use a data set called volunteer. And so we have 2 scores on 2 traits, neuroticism and extroversion. We have a factor for whether the sex of the person was female or male, and then we have volunteer information for whether they volunteer to participate in a psychological study, and it's either no or yes. And notice that we have attached the data set so that later on we can refer to just the variable names without having to refer to the name of the data set. That just makes our t-tests easier to deal with. Okay, so we're starting with the simplest kind of t-test, just the one sample. So the simplest version is the function is ttest. That's just a basic function in R. We don't have to load any package to do that. And then you tell it the name of the variable you want it to test. And so this is using all of the default options. So if we run just this line, then we can see what we get, a one sample t-test, and it knows to do that because we just have the one variable in the parentheses. It gives us the output for the t-test itself in terms of the t-value, the degrees of freedom, and then the p-value, which obviously is very tiny, so you would report this as p less than 0.001. It tells you the alternative hypothesis that was tested against, so the default is to always test it against 0, and then the 95% confidence interval for the mean, so from 12.17 to 12.57, that's a pretty tight confidence interval, so that's good. And then the sample estimate of the mean of x, in which case x is the variable, so that's extroversion. So the mean extroversion score in this data set is 12.37. And then there are various options that we can also include if we want to change things around. So this is just an example of what it would look like if you didn't attach your data set and we're using the full variable name, my data, with the money sign, but since we attached it, we actually don't need that. And if we want to have a one-tailed test, we add this alternative equals and then in quotes greater, and then the other option would be less. So if you were saying that your true mean is either greater than 0 or less than 0, you can also change the value that you're comparing it to. So instead of comparing it to 0, you can compare it to anything else. In this case, I just chose 5. And then the default confidence interval is a 95%, so you can change that to a different percentage. So in this case, we changed it to a 99% confidence interval. So now we can see the t-value again, degrees of freedom, p-value. Now our alternative hypothesis is that the true mean is greater than 5. The 99% confidence interval goes from 12.13 to infinity. And it's infinity on one side because we have the one-tailed or directional alternative hypothesis, and then our sample mean again. So actually if we run both of these at the same time, it's kind of interesting to compare. So you can see that the t-value is quite a bit different because we're comparing it to 0 and then we're comparing it to 5, so that makes a difference. Although the degrees of freedom are the same, the p-values are the same, and then of course the mean is the same. That didn't change at all. Okay, so that's how you do a one sample t-test. And then next we're going to look at the matched samples t-test. So we're going to compare levels of extroversion and neuroticism. So we just put both of those variables after our t-test function. And now if we want to do the matched samples t-test, we have to say that paired equals true. And then all of the other options are the defaults. So here in our output we get a paired samples t-test. It tells you the variables that are being compared. Again, the t-value, degrees of freedom, and the p-value. The alternative hypothesis that the true difference in means is not equal to 0. The 95% confidence interval, and then the sample estimate, and here it's in terms of the mean of the differences between extroversion and neuroticism. And then if we want to look at some options that we can include, we can add an alternative hypothesis of greater or less if we want to look at a directional alternative. And then again, we can change the confidence level. So I've done both of those things here. And so we get this different alternative. The true difference in means is greater than 0. We get infinity in one of our confidence intervals again. And this one now is going to be different than what we had before, because now we're looking at a 99% instead of just a 95%. Okay, and then we can also compute effect sizes, and it would be nice if there was just a built-in function in a package, but there's not. But I found a function that someone had written for the independent samples t-test, and I actually emailed him a couple years ago and said, hey, do you have a function to do this for a matched pairs? And he said, no, it wasn't in the package, but then he sent me this code. So I didn't make this up. This was from AC Del Rey, who was kind enough to share it with me, so we can create our own function for the effect size for a matched pairs T. So we have to run this part first just to tell R basically what we want it to do when we use this TES2 as a function. And part of what we need to know within this function is the correlation between the variables we're comparing. So we just need to use this old basic correlation function to find the correlation between extroversion and neuroticism. So if we run that, the correlation is negative 0.10. And then here's where we can use this function that we already defined. So this TES2, we give it our t values. That was from when we computed t up here. And then we give it our sample size. So we could look at our t output again and get that from the degrees of freedom. And then the correlation that we just computed. So if we give it that information and run this, it will give us the effect size D, the variance of that effect size, and then the lower and upper limits for that D effect size. Okay. And then we have the independent samples t-test. So now we are comparing neuroticism levels for people who did and did not volunteer. So first we want to look at our variance and see if we can treat our groups as if they have equal variance or if we need to account for differences in our variance. So this line just allows us to actually see what those two variance estimates are. And so we're using this very useful tapply function. And then within that, we're saying we want to look at the variable of neuroticism. Our grouping variable is volunteer. VAR tells the function that variance is what we want it to compute. And this means basically don't worry about missing data. And so then what we return is this is the no volunteer group and their variance, and the people who did volunteer and their variances. And you can see that they're very similar. And we can actually compute a test, so we can use Levene's test for equality of variances to actually test whether those differ. So it shows us the degrees of freedom, the F value, and the P value, and this is really what we want to pay attention to. And this is one of the few cases in which we want our P value to not be significant, because we would much prefer that the variables have equal variance, or at least that the variance doesn't differ significantly, because that's one of the assumptions of the regular t-test that we would like to have hold true. And then when we do that, we can then just run the basic t-test. So if we get a p-value of greater than 0.05, we can do our regular t-test. If we get a p-value of less than 0.05, then that's telling us that our variances are different and we need to make an accommodation for that, and we do a Welch test instead of the regular t-test. So I'm going to show you first what you have if you have all default options, so the same t.test function, and this time it kind of looks like a regression formula. So neuroticism is the variable, and then volunteer is the grouping variable, so we're comparing neuroticism for people who did and did not volunteer. And you can see that our default actually is that Welch two-sample t-test. So our default is assuming that our variances are not equal, so that's a good thing to keep in mind. All right, we have our t-value, our degrees of freedom, and our p-value. Our alternative hypothesis is that the true difference in the means is not equal to 0, so that non-directional alternative. we get our 95% confidence interval, which we can see includes 0. And then we get our sample estimate. So instead of giving us the difference between the groups, this gives us the mean for each group. So the mean of the group that said no to volunteering and the mean in the group that yes, they were volunteered. And as you can see, they're highly similar. Right, our confidence interval includes 0. Our p-value is greater than 0.05. So all of this is telling us that these groups don't differ. Okay, and then some of our options. So we actually had equal variances assumed. So if we want to get the regular independent samples t-test, we have to use the option var.equal equals true, so that it will compute it as if our variables are equal. This is where we get just the 2-sample t-test instead of the Welch t-test, but it's telling us the same thing. You know, large p-value, 95% confidence interval that includes 0, and obviously our means are still very similar. They're the same means. Okay, what if we want to do a one-tailed test? So that's a possibility. We add the option of alternative equals greater or less, just like we did in the other tests. Again, we can change the confidence level to something other than 95%. And again, we're just going to do the typical t-test by telling it that our variances are equal. So what changed here is our alternative hypothesis, that the true difference in means is greater than 0. So we have infinity on one of our confidence limits, but still our p-value is huge. There's no difference between the groups. And then last, we will calculate an effect size. So we can use this ttest function in the compute es package, but we have to tell it the t-value, so we can pull that from what we've done here. But we also need to tell it the sample sizes for each of our groups. So to do that, we can just use this basic table function with volunteer as the variable, and it will tell us how many people volunteered and how many people didn't. So it gives us that output, and we can just plug those numbers into our 2 sample sizes. And then you can also, the exact same function, and you can leave out the t equals, n.1 equals, and n.2 equals. You can just put the 3 numbers and you will get exactly the same output. I prefer this top one because then it's easier to remember what everything is, so then when you're going back and changing things, you know what order you're supposed to put the numbers in. So you get lots of output with this function. So the first thing we get is a Cohen's d with a 95% confidence interval. So this is the point estimate of Cohen's d, negative 0.03, and then the confidence interval goes from negative 0.13 to 0.08. You get the variance of that, the p-value, which seems a little odd because the whole point of effect sizes is not to not worry about p-values, but this is the same p-value as you got for the t-test anyway. And then a couple of other things. This is Hedges G, just another effect size that we haven't really talked about before. And then you can also get a correlational effect size, so you can get the R effect size, and the 95% confidence interval. You can also get a Z effect size, a couple of odds ratios, just a regular one, and then a log odds ratio. So this gives you a lot of output, and you would want to pick one of these to report. The ones we've talked about are the R effect size and the D, so I would recommend choosing one of those. Okay, and then the last part is power analysis. So when we do this, we're using the PWR package and the function pwr.t.test. So this is power for t-tests. So two-tailed tests are the default. So if you don't tell it greater or less for the alternative, you'll get just a two-tailed test. And then the other default is for an independent samples t-test. So if you have nothing like we do in this first one in terms of the type of the test, you'll get the independent samples. If you want the type, then you have to include either one dot sample or paired as the type of test. So this is just with the default options. And the way that this function works is it actually has 4 different pieces of information that you can give to it. So you can give it the sample size, you can give it your effect size in terms of D, the significance level, and the power. And you actually only give it 3 of these values, and then it will compute the 4th. So in this case, if we're computing an a priori power analysis, where we have an estimate of our effect size, we know we want our typical significance level and a power of 0.80, If we give it those 3 pieces of information, it knows we didn't give it the sample size, so that's what it will calculate for us. What sample size will we have to make all of these other things be true? So let's run the first one. All right, so it gives you the 2 sample t-test power calculation. These are just the same numbers that we gave it, so that's good. And then what it calculated for us was the sample size for the 2-sided alternative. And a very helpful note that the n is the number in each group. So we're going to have essentially 64 people in each group. Since we have 2 groups, it's going to be double that for our total sample size. And then if we're going to look at one sample, we just need to add the type equals double quotes 1.sample. Everything else is the same. So now we have a 1 sample t-test, and now our sample size is only 34. So that's a lot smaller to have the same level of power in a 1 sample test than in a 2 sample test. And since this is 1 sample, our total sample size is 34. There's nothing to double. And then in our matched samples t-test, so we've just changed our type to pairs. And now our sample size is 33, and that's the number of pairs. So if you have the same people in both of your groups, you need 34 total people. If you have different people in your groups that you can match up somehow, then you would need double that number of total people.